Yeah, so as we were discussing previously about the branch predictions, I mean the control hazards, and in that control hazard, uh, no, we were talking about the different solutions for control hazard. One of the solution is your branch prediction that treated as your speculative execution. So in today's lecture, we try to discuss the overview of the branch prediction and branch prediction algorithms and some advanced branch prediction algorithm, that is two-level algorithms. Then we talk about memory disambiguation and implications of security. So in today, we try to cover the overview of branch prediction and branch prediction algorithms. So let us quickly get into this, the overview of the branch prediction. That we have seen that mostly the control hazards caused by the branches. So the key performance in modern processor that affects they affected by these control hazards. So there are certain solutions which we have discussed in the previous lecture. That one is stalling the pipeline, another one is assume not taken, and another one is the branch delay slots. And but these none of these solutions are the really address the problem. So there is one more solution called the branch prediction, that we'll try to discuss how this branch prediction will helpful to solve the control hazard problems. So as we looked at the in the computer architecture, the branch predictor is a digital circuit that tries to guess which way a branch will go before this is known definitely. So the purpose of the branch predictor is to improve the flow in the instruction pipeline. So the branch predictors play a critical role in achieving high performance in many modern pipeline microprocessor architectures. So that we have observed that two-way branching is usually implemented with a conditional jump instruction, and a conditional jump can either be taken and jump to a different place in program memory, or it can be not taken and continue execution immediately after the conditional jump. This is what we observed in the previous class. So it is not known for certain whether a conditional jump will be taken or not taken until the condition has been calculated at the execution stage in the pipeline, and the conditional jump has passed the execution stage in the instruction pipeline, which we observe. So without branch prediction, the processor would have to wait until the conditional jump instruction has passed the execute stage before the next instruction can enter the instruction fetching stage in the pipeline. So the branch predictor attempts to avoid this waste of time by trying to guess whether the conditional jump is the most likely to be taken or not taken. The branch that is guessed to be the most likely is then that will be fetched and speculatively execute. So if it is later detected that the guess was wrong, then the speculatively executed or partially executed instructions are discarded, are flushed out from the pipeline, and the pipeline starts over with the correct branch, incurring a delay. So the time that is wasted in case of a branch misprediction is equal to the number of stages in the pipeline from the fetch stage to the execution stage. Thus will be mispredicted. So modern microprocessors tend to have quite long pipelines, so that the misprediction delay is between like 10 and 20 clock cycles. So the first time a conditional jump instruction is encountered, then there is not much information to base a prediction on it. So that we try to check it in this branch prediction. As said, this is one of the best solution for control hazards in the branch prediction. So what it is doing, this branch prediction predicts whether the branch is taken or not taken. And if it is taken or not taken, but the address of the branch target must be calculated, right? So the prediction is then used to fetch the next instruction from the memory and uh, give as an input to your pipeline. And this is what we have discussed. If the prediction is correct, then the instruct pipeline execution stages go smoothly, or else all the instructions which are there in the pipeline at different stages must be flushed out. So the branch prediction is not the perfect, but if the prediction result is wrong, then as we said, the pipeline has to be flushed out. So almost every design decision changes if we have the perfect rather than the realistic branch prediction. So by let us just consider a C code and its corresponding assembly code and try to check how it will affect the performance of your CPU based on this prediction. Suppose if you have the code, if R is equal to 2, then store this value 0 into R1, else store the 2 into your R1, and then the next instruction store the value 3 into R2, right? So in this case, let us see, are you following me? Are you following me? Okay, that's good. Yeah. So in this case, now let us see here if this small piece of C code converts into your assembly language, then you will find that the first R is equal to 2, so the comparison will be happened here. So this comparison takes place first in the assembly code, that compare R1 is equal to 2 or not. Then the condition comes, the if condition comes, that after that comparison, jump not equal to L1 level or go to the target, that is the target address. As we discussed, the branches have two alternative solutions in the conditional branches, right? So go to the target, that is L1, or else go to the target, another target, your L2. So jump not equal to when this comparison is not equal to, then go to your L1, or else you start executing these these instruction. And if this is not, then go and execute this instruction, and then followed by this instruction. Correct? So here you can see from this what you call assembly code, we are interested in to find out how the control hazards are happening, and because of what? Because of the branches. So what are the branch instructions here? To predict whether it will be going inside the if condition or going to else condition, that is based on this branch instruction, based on this branch instruction. So in this branch instruction, that is what we are saying, that the first time a conditional jump instruction is encountered, suppose in this if R equal to R1 equal to 2, then there is not much information to base a prediction on it. So, but the branch predictor keeps a record of whether the branches are taken or not taken. So when it encounters a conditional jump, that has been seen, suppose several times before, then it can be, base the prediction whether this branch will be taken or not. But in this case, if you see this in this branch predictor, predicts that this branch instruction will be taken or not taken. So it is also predict the branch predictor also predicts the target address. So it can be the target address which is there in your program counter. We call that your relative address or the effective address of that. But from this, the branch instruction, we the prediction for this branch is essentially just a guess that it will consider it, or 1 is equal to 2 will be considered. So as there is no there is no much information, having only the very limited information to aid us in this prediction that whether this branch will be taken or not taken. So, and let us see another example for considering the inner loop. I mean the for loop, where the equivalent condition of this for loop. I mean the assembly code for this for loop. You will find that. So first, it will move the value 0 into your R1, and then it will enter into the target code, where it is going to be executing, that is L0. Move 0 into L1, then go to the target address or the PC relative address L1 and start doing operation. So in this operation, from this assembly code, if you check the jump, the conditional jump, or you can see the branch instruction in this assembly code is at your J1 equal to L0. So previous a few of the instructions are executed, then here at this J1 is equal to 0, it is going to, this branch instruction will be predicted by the branch predictor, and it will also label or try to find out the target address, try to calculate the target address or the effective address of this branch condition, a branch instruction, that is L0, and that address will be available in the insert into your program counter address. So in this case also, this is first time this branch instruction is encountered. So we don't have any previous information whether this branch will be taken or not taken. So again, for the first time encounter, it is just a guessing process only. So, but for the future execution of this branch, it is the first time it is just guessing that go to L0 target, and from there it is going to compare the condition. When this condition satisfies, then in the future it will be, this branch will be considered as will be taken. So we can use the past taken or not taken history and the past branch target address to guess, to predict the future execution. But at the first time, we don't have any information whether to go to this target address or not. So when this kind of the problems comes, there your control hazard arises. So how to solve this kind of problems then? So the branch prediction is not the same as your branch target prediction, but the branch prediction attempts to guess whether a conditional jump will be taken or not. So branch target prediction attempts to guess the target of a taken condition or unconditional jump before it is computed by decoding and executing the instruction itself in the pipeline. So branch prediction and branch target predictions are often combined into the same circuitry. So that is what the branch prediction algorithm says. So in the one of the branch prediction algorithm is dynamic, the hardware, branch prediction. As we are saying, branch prediction is a digital circuit part. So in this, as we just explained, the branch behavior is monitored during program execution only. But first time it is completely a guess, but after second time, if it is a loop, inner loop 1 or loop, suppose, then the future execution of that branch will be predicted based on its previous history. So this branch instruction executions has taken two tasks, as we said. One is your conditional evaluation, as we said, the comparison of your R1 is equal to 2 or not in our previous example. So that is the conditional evaluation. In for loop also, the condition will be evaluated, that is R1 is less than 10 or not in this example. Whether this condition based the condition evaluation, based on this condition evaluation, the target address, it is going to the same target location or going to the new target location will be calculated. So that is the target address calculation, where to go when it is taken, go back to the previous location, or where to go if it is not taken to any new target location. So these are two important tasks will be performed by the branch predictors to execute the branch instructions. So the target prediction also applies to the unconditional jumps, as we said, right? And the branch direction prediction is most important in this, whether it is going to take back to the same location, or it is going back to the same location or going forward to the next location. So there are three levels of complexities are there in this. So that is the branch history table will be maintained. That history table maintains the history of the branch, whether it is taken or not. First time it is completely guessed, but after that, in the previous history, whether it is taken or not taken, that information maintained by the branch history table. And from this branch history, and another one is a two-level table is used to maintain this dynamic branch history. In two-level tables is the branch history table will be there. Along with that, another table will be maintained, whether it will be taken or not taken. So in branch history taken, if a branch is taken, suppose n times, that n times data will be maintained. The history will be maintained. Sometimes the branch may be taken, sometimes may not be taken. So entire history will be maintained. But in two-level table, it gives at a particular time, at a particular iteration, whether that branch is taken or not taken is predicted by a two-level predictor. And then sometimes the combination of independent branches and the inner loop branches will be there to predict both the branches. It takes the hybrid the predictors. So to make this, the dynamic branch prediction is used. So the dynamic branch prediction uses information about taken or not taken branches that is gathered at runtime to predict the outcome of the branches, So let us see this with an example in the branch direction prediction, whether it will be taken or not. So the basic idea in the branch direction prediction is the hope that the future behavior of the branch is correlated to the past behavior. So this idea works well for the loops and the error checking conditionals. So for a single branch program counter, it can be implemented. This branch direction can be implemented in a single branch prediction with the simplest possible idea of keeping the 1-bit saturating counter and 2-bit saturating counter. So in 1-bit saturating counter or 1-bit around to indicate whether the branch the most recently that branch is taken or not taken. That means it keeps the only one previous history. That this 1-bit saturating counter records the last outcome of the branch, not before last, and like that. So this is the most simple version of dynamic branch predictor possibly, but although it is not very accurate, so to make a little bit accurate for predicting the branches, it takes this idea, the branch direction prediction keeps 2-bit saturating counter or 2-bit rounding. So in this 2-bit rounding, it maintains this 2-bit saturating counter or 2-bit rounding is a state machine. Actually, it is a state machine. So in this state machine, it will have the states. So this state machine with the 4 states will be there in this 2-bit saturating counter. So what are those means? The first one is the strongly not taken. Strongly not taken. And second, state is weakly not taken. And third one is weakly taken. And fourth one is strongly taken. Strongly taken. So these 4 states maintained by this state machine for 2-bit saturating counter. We will discuss this in detail. But when a branch is evaluated, the corresponding state machine is updated. So we'll talk more about this by after looking into the 4 conditions. But this 2-bit saturating counter maintains this state machine, and that state machine is having 4 states. So let us say this with an example of 1-bit branch direction as well as your 2-bit branch direction. So let us consider the a loop for I is equal to 0 and I less than 4, I plus plus, and the inner loop is for j is equal to 0, j less than 4, j plus plus, and then it ends. So this, so now we need to find out this branch direction, whether it goes back or whether it goes forward. So in this case, from this, let us find out the actual outcome of this branch. Actual outcome of this branch. So in this, for I is equal to 0, gives the actual branch outcome. When you are executing this program, the actual outcome which comes here is, for I is equal to 0, you will enter into the inner loop, and inner loop will run, the j is equal to 0, j is equal to 1, j is equal to 2, j is equal to 3, up to j is equal. And when it reach to the condition j plus plus is equal to suppose 4, so there the condition will be fails, and this branch will exit and go back and increase the I plus plus and check this condition, and then again it will enter into this loop, correct? So in this case, the actual output or the branch actual outcome is, for I is equal to 0 and j is equal to 0, the branch will be taken. For the j is equal to 2 also, the branch will be taken. 3 also branch will be taken. When it reaches to 4, the condition will be failed, and the branch outcome is not taken actually. Correct? So are you getting the point? Good. Okay. So this is the branch actual outcome. So for the second iteration, when I is equal to 1, then again it entered into the inner loop, and the branch outcome is for the j is equal to 0 to your j is equal to 4. It again takes the branch will be taken at j is equal to 0, j is equal to 1, j is equal to 2, j is equal to 3, and at j is equal to 4, the branch will not be taken because the condition fails here, this condition. Similarly, it goes for the next iteration, I is equal to 2. then I is equal to, at I is equal to 2, again the j values will be find out taken or not taken, and this loop, outer loop will run up to I is equal to 0, then inner loop also run, and inside inner loop that branch is taken or not taken. When I reach to 4, the condition fails and this branch will not be taken, and it goes to the new target. So in this case, in this branch 1, when it is reaching to the 4, so that branch inner loop is not going to be taken, and the direction flow back to its parent branch, and there again it start executing. So this is the branch actual outcome. So what the 1-bit branch direction predicts is, in 1-bit branch direction prediction, it predicts by considering its one previous record, whether it was taken or not taken in actual branch outcome. So that is the hardwired prediction, that is the branch prediction. It is a hardware circuit, that is what we are saying. So how it is going to be predicted based on the actual outcome or branch outcome means, in 1-bit prediction, after one wrong prediction, then the predicted bit is inverted. If it is predicted as taken, then inverted to not taken. If it is predicted as not taken, it is inverted to taken. And initially, this algorithm starts with the assumption that the prediction that the branch is not taken. The branch is not taken. So let us see this. In the branch history table, it maintains, the branch history table maintains that the first it is not taken. So it starts with this 0. If branch is taken, then that represents with 1 in the branch history table. Okay. So in the branch history table, so let us have a table here. In this table, the assumption is for I is equal to 0, the hardware prediction assumes that for I is equal to 0, and when it is entered into the inner loop, it is going to predicting the inner loop that for j is equal to 0, first time in 1-bit prediction, it assumes that it is not taken. The assumption is not taken in the table, branch history table, not taken. Okay, but so it assumes that it is not taken, but actually it is taken. Actually it is taken. So there is one wrong prediction. There is one wrong prediction here, right? So it is not taken, assuming, but actually it is taking. So there is one wrong prediction. When it is one wrong prediction is there, then it is converting, invert this not prediction to your prediction part. Invert this not prediction to the prediction. So in this history, you will see starts with not prediction, then it's invert that bit into your prediction as taken. So actual is also taken, so it is a right prediction. Then it go with the prediction previous history is not taken, so again it will predict in future that taken, and the actually also it is taken. That's a correct prediction. Then by using this previous history in the next iteration, it assumes that it will be taken. Okay, so then in the actual also it is taken. So in future also, it assumes that the hardware prediction assumes it will taken. Okay, but actually it is not taken. So in the branch history table, it maintains that it starts with not taken, then it's converted into taken, 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 and then taken when it is, this branch is taken history. So by using this previous history, it is going to predict the next history for I is equal to 1 and your j is equal to your 0, 1, 2, 3. It predicts that initially it is, the previous one is taken, it is the taken, but actually it is not taken. So it start predicting that in future it will not be taken. But actually it is taken, so then it inverts from not taken to taken. So then it assumes that it will not be taken, but it is Actually, it is taken. So the sequence maintains that 1, 1, 1, and 1. So this continued for the next iteration also. So this is a hardware prediction. In next iteration also, it assumes that the previous records is taken, but actually it is not taken. So there is a wrong prediction. So it inverts that taken to your not taken bit. So that is not taken. And from there, it continues again, the sequence is followed the same way. So like this, the branch history table maintains all the occurrence, the previous history of the branch, to predict the future prediction. So that happens same with the next iteration also, right? So are you getting? Yeah. So in this prediction, the total occurrence of this branch, or total execution of this branch happened 16 times, right? 16 times. But out of 16 times, based on this hardware prediction, in every iteration, there was 2 wrong predictions. So, and 3 right predictions were there. So in that case, in total, it is giving 8 wrong predictions, and it means around 50% of the predictions are taken and 50% of predictions are wrong here. So when 50% of the prediction wrong, and in that case, that instruction which is taken inside the pipeline must be flushed out, So this is also, this is one of the branch direction prediction, but as we said, this is not giving the accurate result or the precise result, or what you call the very accurate result. So then, it goes for the 2-bit saturating counter, so where that can maintain more history. Okay, so let us see that 2-bit saturating counter. Okay, so for the same code, you can see the branch outcomes which we have just observed. Based on that, how this 2-bit saturating counter works means it takes the in the hardware prediction, it takes 2 bits. It takes 2 bits instead of 1 bit. It takes 2 bits. So it starts with the initial history table contains 0, 0. It starts with the 2 wrong predictions. This algorithm starts in 2 wrong predictions. After 2 wrong predictions, compared to your actual outcomes, then it invert its prediction from not taken to taken. So it says that when a branch is evaluated, the corresponding state machine is updated. We'll talk about the state machine. So the branches evaluated as not taken change the state towards a strongly not taken, and branches evaluated as taken changes to the strongly, towards a strongly taken. So the advantage of this 2-bit counter scheme over a 1-bit scheme is that a conditional jump has to deviate twice from what it has done most in the past before the prediction changes. So let us see that, as we said, it starts with 2 wrong predictions. So for the first iteration, when it goes into the inner loop, in the inner loop for j is equal to 0 to your 4, first it starts with not taken. First it starts with not taken, and then it compares this not taken with this actual outcome. In actually it is taken, so 1 wrong prediction here. And again it goes with another iteration also. It assumes that this branch will not be taken, but actually it is taken. So second time again 1 more wrong, so 1 plus 1, 2 consecutive wrong predictions are there. So then it change its prediction bit from not taken to, or change its status from not taken to taken. Then this taken compared with the actual outcome. In the actual outcome, it is taken. So it is a correct prediction. then it will keep the same thing. When there is a correct prediction, the bits will not be inverted. So in the next prediction, it assumes that previously it is taken. So in the future also it will be taken, and in actual outcome also it is taken. So then it is again the correct prediction. So then it goes on, assume in the fourth iteration that it will be taken, but actually it is not taken. So this is now one wrong prediction. This is one wrong prediction. But in a single wrong prediction, your hardware circuit or your 2-bit saturating counter will not reflect. Okay. So in the next iteration also, by using the previous history, okay, for the inner loop, it assumes that in the previous history, it is only one wrong prediction is there. So it assumes that that prediction is true, I mean the taken. So it assumes that it will be taken. So then that is compared with the actual outcome, it is matching. So the prediction is correct. Then it go ahead, it continue going on, predicting that it will be predicted and compare with the actual outcome. But at the fourth iteration, the hardware prediction predicting that 2-bit saturating counter predicting that this will be taken, but actually it is not taken. So there is only one wrong. So it is not going to change its what is the prediction bit. So in the next iteration, it continue with the taken only. The branch will be taken again in the I is equal to 2 and j is equal to 0, and that prediction will continue. So are you getting this point? No, for every iteration, it use its previous record, the branch previous record, whether it was taken or not taken. Based on previous record, it is going to reset or it will continue with the same in 2-bit, 2-bit saturating counter. So in the history table, it maintains the previous record. Based on this previous record, it is predicting that in the future also this j is equal to 0 time it will be taken again. And then it compares with the actual outcome. When it is matching, that means it is a correct prediction. Yeah, it only inverts the bits when there are 2 consecutive wrong predictions comes from the previous history. Does each for loop have its own branch history table? Yeah, every branch having their own branch history loop. Every branch, because your program counter holds the address of only one branch history table. When it is entered inside the branch, then your program counter holds the address of this inside branch only. So for this inside branch, one history table will be there. For the outside branch, one history table will be there. Yeah. So this will continues for all the branches. I mean, all the iterations in the same fashion. So then if you compare the number of wrong predictions for the entire execution of this loop, from the history table, you will get how many the accurate predictions that this hardware is given for and inserting these loops into the pipeline means from here you find total 6 wrong predictions are there. 6 wrong predictions. So it is giving a better the accuracy compared to your 1-bit saturating. So in that way, so the number of wrong predictions are reduced. So the number of right predictions are more. So the branch instructions which are taken into your pipeline will successfully execute and come out of your pipeline. So here, the first 2 wrong predictions, then the last prediction is wrong 3. And in the second iteration, only one wrong prediction 4. And in the another third iteration, only one wrong prediction, that is 5. And in the last iteration, only one wrong prediction, that is 6. Whereas in 1-bit saturating counter, we find that the 8 wrong predictions. So this is how the branch prediction algorithms, they use this this dynamic branch prediction as stated. That dynamic branch prediction uses information about taken or not taken branches gathered at runtime to predict the outcome of your branch here. So based on this, now let us take one more example of this. Based on this example, let us try to build a what you call the history table, or the state machine table, which maintains the states. So in 2-bit saturating counters, as we said, it is a state machine. That state machine having 4 states. So this 2-bit history means the prediction must miss the twice before the change. So in n-bit predictors are possible, but after 2-bit, there is not much benefit in that one. So in this 2-bit saturating counter, as we said, it will maintain the the state machine. So in that state machine, we are saying that 2-bit saturating point means you are 2 to the power of 2, it gives 4 states. So in that 4 states, because every state uses the 2 bits, so if it is 0, 0, that means it is strongly not taken. Previously, it is strongly not taken. If it is 0, 1 means it says that it is weakly not taken. Weakly not taken. If it is 1, 0 means it is weakly taken. And 1, 1 state means it is strongly taken. Strongly taken. So as we said, in 2-bit saturating counter, the algorithm starts with the prediction that predict that not taken strongly not taken. But after that, if it goes on, if it is taken, suppose if you consider the previous example, it starts with strongly not taken, but actually it is taken. So it goes to the next state, and it based on that actual output and the prediction, the state bit saturating counter will be updated. So there are 4 states, as we said. Then it starts with the strongly not taken, but actually if it is taken, suppose, then it enters into your likely not taken. And again, in the second term, we have seen, again, assume that not taken, but it is taken. So it is going to a strongly taken term. There, the 2 consecutive wrong predictions are there. So then it is changed its bit inverted from your from your not taken to taken, from NT to T. And after that, in that prediction, it is taken, but when it is in likely not taken, that means predict it is weakly not taken. And again, the actual output is also, suppose the actual branch outcome is also suppose not taken, then it goes into the next step that it will strongly not taken. And but if it is taken, when it is in the predict, it is taken, and again it is taken, then it will be remain in the strongly taken one. And if it is not strongly taken one, and the prediction is strongly taken one, and the actual outcome is suppose not taken, then it will go to likely the predict taken, or weekly predict taken. And when it is weekly predict taken, but actually if it is not taken again, then it goes to strongly not taken. If it is taken, then it goes back to your predict taken. So your 2-bit saturating counter maintains this 2-bit status based on whether they are taken or not taken. Okay. So with this, let us see an example of saturating bit counter here. So see, the 2-bit saturating counter or your state machine in going to be updated. The state is going to be updated based on the hardware prediction and compared with your actual outcome. So are you following me? Good. Okay. So is that, are you getting this point up to now? Is it clear? Good, good. Okay. Thank you. Yeah. Okay. So now see, to build this state machine, a 2-bit saturating counter, initially, as per your 2-bit saturating counter, initially your state machine starts with the 0, 0. Okay. Assume that it is not taken. Okay. So then your hardware prediction or hardware prediction, dynamic prediction, it starts with the algorithm initial that the branch will not be taken, not taken. Then it compare that not taken prediction with the actual prediction, the actual outcome. So actually it is taken. So there is a one-time wrong prediction here, one-time wrong prediction. So now, by just recalling your saturating counter state machine, when it is 0, 0 and not taken, then but actually it is taken. So from your 0, 0, it is going to the next state, that is your weekly not taken, status. Then your branch prediction goes for the second step, that second time also the branch will not be taken, because only one time it is wrong here in the first case, in the first guessing. So second time also it is guessing that it will not be taken. It will not be taken. So this is compared with the actual branch outcome. Actually, it is taken. So from 0, 1 state to taken, the taken, okay, it leads to your 1, 1 state in the previous case. If you see this, sorry. So initially it is at 0, 0 state and predicting that it will not be taken. But actually it is taken, so entered into the state 0, 1. And after that, again, the branch prediction assume that it will not be taken. Not taken, but actually it is taken, so goes to the next state, that is your 1, 1 state. Okay. So that is what here we have seen, that second time also assumed it is not taken, but actually it is taken. So then two wrong measures are there, but from 0, 1 state it is taken, so it will enter into the next state, that is 1, 1, strongly taken. Strongly taken. What do the blue arrow means in the state machine? The image. Which one talking about? So these blue, you're talking about these blue arrows? Yeah, these blue arrows are taken, that the actual not taken, the actual outcome of your what you call the branch is not taken. If it is taken, then we use the dotted line for simple understanding. If not taken, we are using the blue line. Is that clear? Okay, so now we are at this machine now. It strongly taken. So there are two consecutive wrong predictions are there. So after that, your the hardware prediction change or invert its bit to taken, change its prediction to taken. Now this prediction is compared with the actual branch outcome that is taken. So this branch prediction is true, and now you are at state 1 1, and actual what you call the branch outcome is also taken, so it will remain in the same state again. So by using previous history, your branch prediction predicts the future, that in future also it will be taken. Then the actual outcome is taken, so that is the correct prediction. Then it will remain in the same state, strongly taken state. So then based on this, the previous history, using the previous history, your prediction predicts that it will be taken in the future. And it is compared with your actual branch outcome, it is taken, so there is a right prediction. So at the strongly taken state with the actual branch outcome is taken, then it will remain in the same state, remain in the same state. Then your branch predictor use this previous history and try to predict that it will be taken again, will be taken. So then compare with the actual outcome. So it is matching. So correct prediction it is. So now your state machine in 2-bit saturated counter, your state machine at strongly taken state, and the input for that state is taken, then it will remain in the same state. It will remain in the same state. So for the future prediction, your branch is predicting using the previous history and assuming that it will be taken. It will be taken. But actually it is not taken. So again, there is one wrong prediction. Again, one wrong prediction. So like this, based on the branch actual outcome, your state machine will update the entries in which state it is, whether it is taken or not taken. 1 1 means it is strongly taken. 0 0 means strongly not taken. Your 0 1 means weakly not taken. Your 1 1 means strongly taken. 1 0 means weakly taken. So this saturating table, this table is used for the future prediction of your branch, future prediction of your the branch. So this is how the 2-bit saturating counters works. So at this point I'd like to stop. Tell me, are you understood this concept? This is very important. Okay, very good, super. So now let me quickly ask you the question. Okay, so now it is taken, the prediction is taken, but actually it is not taken. So then what will be the entry in the state machine? What will be the entry in the state machine? Very good, super. Yeah, so that will enter into your 1 0. That is weekly taken, weekly taken. That is good. Okay. And after that, suppose if it is taken, the actual outcome is suppose taken, then what will be the prediction? What will be the prediction? Prediction is one strongly taken, strong. Okay. No, the prediction will be using the previously only one wrong. It is. So it assumes that in future also it will be taken. So the prediction will be taken only. So when the prediction is taken, then it compares with the actual one. It is taken, so it is matching. Actual prediction is there. So now, what will be the next entry in state machine based on this state? Yeah, the next state will be 1 1. It will end because from 1 0 it is taken, so it come back to you are strongly taken. Okay, superb. Yeah, so this is what the dynamic branch prediction. So from here, from this, I'm happy that you are giving answer and all the answers are correct in the chat box. That means I'm happy you followed the topic. You understand completely. Okay, so from this you can see that what is the accuracy of this branch prediction for the can you find out the accuracy of this branch prediction? Can you give the answer, please? I think you guys are following slides. Okay. See, there are total how many? It is 1, 2, 3, 4, 5, 6, 7. Out of 7 predictions, out of 7 predictions, okay, how many predictions are correct? 1, 2, 3, 4. So 4 predictions are correct. So that gives the accuracy, branch prediction accuracy. So if out of 7 times, 4 times it is predicted good, that means it improves the performance of your processor in this fashion. Correct? Okay. Yeah. So this is how the control hazards comes and how those hazards will be solved. The solution for control hazards means one is stalling your pipeline where the lot of cycles are wasting because most of the instructions are in stalling. To decide whether the branch will be taken or not, that will be decided at the end of your execution stage in the pipeline. So that is not giving good performance. So the alternative solution which we have found is the assume not taken. Assume not taken. In that case, the next instruction is allowed into your pipeline to give to start executing that one. But that is also not if branch is taken at the decision is taken at the end of the third stage, then the second instruction which is inserted into your pipeline will continue executing. But at the end of the third stage in the instruction implementation, if decision says that branch will be taken, then in that case, the second instruction which is inserted in the pipeline will be flushed out. Okay? And another one which we have seen that the branch delay, in that the same assumption we are assuming that in the read after write we have seen that the decision whether it will be taken or not, to check it out, what happens, the decision will be taken like adding few more additional functional units at the instruction decode stage, the decision will be taken, so there will be only one stall will be there, right? In that case, second instruction will be allowed into your instruction fetching cycle, but not allowed into your instruction decode cycle until the decision will be taken, assume that whether it will be taken or not taken, so that one stage of functional units will not be used by your second instruction. It will enter into instruction fetching cycle and wait there. So that is a delayed slot. We have seen that. Okay. And the fourth one, we have seen that this speculative execution means the assumption, it is prediction. So in this branch prediction, one way is predicting one bit history, previous history, predicting based on one previous history. In 2-bit saturating is predicting based on previous two histories, In that, the performance which is giving better means your 2-bit saturating counters are giving the better performance. Whereas your branch history tables, they maintains the history of the branch. If the branch is running n times, suppose if the branch is running n times, that in that n times, your branch history table maintaining how many times it is taken, how many times it is not taken, how many times it is taken, how many times it is not taken. So that will be maintained in the branch history table. Okay. So based on this branch, this entry, whether it will be taken or not taken, that entry is, depends upon its previous two history, by predicting the previous history, that whether it will be taken or not taken, right? So this is the somehow 2-bit saturating counter. Yeah. So the which one is playing an important role in this branch prediction means your branch prediction buffer. So in the branch prediction buffer, the branch, we also call it as your branch history table, BHT, as you said. So how it works is, just see that the branch history table is just, like your 2-bit saturating point. Based on that, the branch history table works, that there is a 2-bit, whether it is taken strongly or not taken strongly, or weakly taken or weakly taken, that entries will be there in this table for every iteration. So in this, how it is going to be defined means, for any branch instruction, that branch instruction address will be stored in your program counter. Branch instruction address stored in the program counter. So we talk about this address line. We also called this is as your address line or cache line. We talk more about this cache line in system architecture when we talk about the cache memory. But as of now, you understand that this cache line size or address size is 32-bit. So the instruction, branch instruction, the branch instruction address will be stored in this program counter. Based on this instruction, whether it is going to be taken or not taken will be predicted by the branch predictor. So for that, it used the lower 12 bits. So these lower 12 bits are used for the index of this 2-bit saturating counter. So we'll talk more about from this lower 2 bits, it use lower 12 bits, and remaining bits are used for the target address and other address purpose. But in this small cache memory, the lower 12 bits will be used. These lower 12 bits are based on this lower 12 bits. The index of it is going to identify the row in this 2-bit array, a 2-bit small cache memory. We call this as your entry index. This address is the index of this 12-bit, which gives the address of your index here. Let me just write the index part. The index. So based on this index, the entry will be identified whether this branch at that iteration is taken or not taken based on that entry. Taken or not taken will be, given from this table, right? So are you getting this point? In the program, there will be the instruction. In the program, there will be the instruction. That instruction is suppose the branch instruction. So branch instruction means in our previous example, we have seen that jump not equal to. So for this branch instruction, there will be an address. This instruction address will be there. Okay. In that address will go and store in the program counter. From that program, that is your 32-bit address. So from that 32-bit, the lower 12 bits are used for the indexing purpose of the 2-bit saturating and count buffer. In that, whatever entry is there, that entry indicates whether that branch is previously taken or not taken. Based on that history, it will predict that it will be taken or not taken. That the branch prediction will happen on this. Okay, so this is what the branch history table. So in this branch history table, it is a small indexed with the lower bits of your branch instruction address, as we said. So why the lower bits are used means not only the this 2-bit saturating counter or this branch history table is in that particular row. If any row is there, this is just 2-bit dimensional. Like that, in our cache memory, another entry will be there, another table will be there. So 2-bit saturating counter every time. So in that, it is going to find there are multiple. This is for one branch at that iteration, whether it is strongly taken or not taken. In another time, it may be strongly taken. Another time, this entry says 10 means strongly not taken. So in that row, it is going to identify first time whether it is taken or not taken, second time whether it is taken or not taken. So this entire thing is known as your branch history table. In our previous example, every iteration runs 4 times. So there will be 4 2-bit saturating counters in that branch history table. This is one. This is similar to this. Another branch will be there for second iteration of your 2-bit saturating counter. Another iteration will be there. So based on this instruction address, the lower 12 bits are used to identify the row. In that row, in the first iteration, what is its status, whether it was taken or not taken. Whether it is strongly not taken, then it is suppose weakly taken, then it is strongly taken, then strongly taken. So based on this, these previous two histories, strongly taken and strongly taken, your branch prediction, your branch dynamic branch prediction predicting that it will be taken. It will be taken. Yeah, don't worry about that one. That is what I said. This is a 32-bit addressing, cache line address. Out of 32 bits, some bits are specified. So the lower 12 bits are basically used for the entry or index purpose of your this branch history table. And the first lowest 20 bits are used for alignment purpose, then remaining 2 bits are used for the indexing purpose. So there are purpose, every bit field bit position is there is a meaning that we will discuss in the cache line. As of now, you please assume that these 12 bits are used for the indexing of your branch history table. Is that clear, Rami? Yeah, good. Okay. So like this, if 12 bits, all the 12 bits are supposed used for indexing, then in one 2-bit saturating counter, maximum it will have the entries of 2 to the power of 12. So 4096 entries will be there. That means 4096 iteration results are branch, the entries will be kept in one branch history table. Okay, so this is what we said, the why the lower bits are used means the same row can be used by multiple branches to store their 2-bit saturating counter states. So that's why the index bits are, lower indexes are used. And the branches sharing the same lower bits that share the same branch history table entry, thus the interference here. So the implementation of this branch history table is a 2-bit which is attached to each block that gives whether it will be taken or not, as we just discussed. So this address is the instruction address will store in the instruction cache, or the program counter which is hold that comes from your instruction cache. So from that instruction cache, that is these 32 bits will be separated to identify the exact location of your instruction. That is a the in-depth discussion we will do in the when we talk about the cache memory. Okay, so this is about the branch history table. In the next class, we'll try to discuss the along with this branch, the branch target address is also required. So that target address will be stored in similar way in a small the cache memory, which is similar to your the branch history table. So that will hold the address of previous target address where it was there. So by using again the same lower 12 bits to use for your previous target address entry in the branch target buffer, and from there it will get the it will predict the branch target address for the future. Okay, again it will have the same number of entries. So for every branch prediction branch history table, it will be associated with the branch target table, branch target table. So that will also work in the similar fashion of that. So with this, I would like to stop this session. In the next session, we'll try to discuss the the advanced branch prediction or 2-level branch predictions in the next class. So if you have any questions, please feel free to ask me, or else we can disperse and meet you in the next class. Thank you so much for today's. These slides are also different than the one posted, and no, these slides are already updated. Please recheck it. These are the updated slides are already posted on the canvas. Please check it out under speculative execution. Yeah, thank you. See you in the next week then. Yeah. Is there more specific name for the kind of 2-bit saturating counter you described here? No, it is the same name will be used. 2-bit saturating counter. 1-bit saturating counter, 2-bit saturating counter. Please follow my teaching material. I just downloaded them and they are the same. Okay, thank you. Yeah. Let me again cross check. If not, I will update again. Ashina. Yeah. Yeah. Thank you.